of interval whenever s is less than 0 or whenever s is greater than 1. And when it is less than 0, it is in this interval there, evident. So we have this opposite inequality. This is a short story about this very important power moment. And we research something a little bit different. You will see. The object of our research is this lambda, depends on s, is defined like this. So you have the difference between those moments from before. The difference divided by this s multiplied by s minus 1. This is the definition of lambda. And it is defined whenever s is not 0 and s is not 1. Evidently. When s is 0, we defined it as a limit when s is tending to 0. S is tending to 0, you calculate and you obtain this. When s is 0, it's defined like this. When s is 1, it means that s is tending to 1. When s is tending to 1, this limit is this. So we have a definition of the function lambda for each s, each real s. And it happens that this function lambda has many interesting properties. Let's see. First of all, is this property that lambda is always greater than 0. Why? Because of this Jensen's inequality. When s is greater than 1, this quantity is positive. Okay. But this quantity up there is also positive because of Jensen's inequality. Yes? So, in this case, when s is greater than 1, it is positive. When s is less than 0, then this s minus 1 is also positive, and this one is also positive because of Jensen's inequality. This is between 0 and 1. Then this is negative down there, but up there is also negative because of Jensen's inequality. All in all, it is positive. So the first property is that lambda is always positive. And the second important property is that lambda is logarithmically convex in S. What it means? Function is convex. No, but when the function is convex. And we say that the function is logarithmically convex if its logarithm is convex. Is it clear? So, what we obtain? We have a function f is this logarithm is convex. I mean, it's not convex. We have function f, that this logarithm is convex. When you put it there, we have the logarithm f of x plus logarithm f of y. 2 is greater than logarithm of x plus y. And when we do some operation, we get that this multiplied at f epsilon is greater than f squared of x plus epsilon. This is the property of logarithmically convex function. And now, evidently, each logarithmically convex function is also convex, but the contrary is not true. So, logarithmically convex functions, they make a subset of the set of convex functions. This is this property, you see, of logarithmically convex function. This is over there. And we denote it like C of St, and St is on some interval where those moments exist. Exist in the sense that they are finite. This is the function C. And some other thing is that in some paper file, you will see it afterwards, we wrote this mixture of Jensen-Lyapunov inequalities. It says that for any RSD in this direction, we have this inequality. More than that, in another paper, we proved that if R and T are even natural numbers, and S is an integer between them, then this inequality takes place for all probability distributions which could be negative also. Could be defined on negative part of real axis. It is proved on the paper 6. We will see after that. And now, our investigation goes further, and we investigate those entities here. We said that logarithmically convex functions are also convex. So, this function t is greater than 0 because lambda is convex. This is always greater than 0. And now we investigate this quantity here and obtain 4 parameters inequality of second order. So this is inequality of first order, elementary first order. Inequality of second order says this. This is theorem 1. So for this function we have that this multiplex is always greater then this difference on square. For each S and T from this interval where moments exist. And so we have some corollaries that this function is always log convex, and so on. Another result is that if P and Q are arbitrary positive numbers, then this function W is defined like this. We have this property. So it is log convex in for those variables, S, T, U, and V. This inequality takes place for each of them. So you see, this paper is from Acta Mathematica Hungarica. It's a very good journal on scientific index. And it's published last year, so this is fresh knowledge. Further, we have another second order inequality. Recall that C was what? Here was this multiplication variant. See the definition of C? This is C, and now we have an inequality of second order for this function C of two variables. And it says something similar. This is for convex function, you see, and something similar is valid for multiplication. So, this entity, we name it like this, is always greater than 0. So this is greater than this on square for each value of parameters. What is interesting is that this inequality, that this is greater than this, is very sharp. Sharp in the sense, it is this in the remark, that if we have simpler case, that we have only two variables, x and y, and those P and Q, those variables, look there. So, the simplest variant is that P of x na s is equal to P x na s plus Q y on s. And E of x consequently is Px plus Qy. This is the simplest case, and s is equal to 2. In this simplest case, we have that this function, and then we put that s is equal to 2, 4, 2, 6, and calculate all of this, we obtain something like this. Constant, which depends on P and Q only, x minus 1 on 14 degree. And this constant, you see how small it is. So, it means This inequality above is very precise. It doesn't is worth only for those parameters, but it could be proved that for any parameter. Do you have this? You see, it means not only for 2, 4, 2, 6, but for any phi of ST UY is constant of x on epsilon of 14 degree. If x minus y is less than epsilon, epsilon is some positive number. And in some cases, it's even constant multiplied by epsilon 16 degree for some value of those parameters STU. So it is very precise. So we didn't stop there and go further, and what we make. Now remember this definition of the function phi. We make inequalities with the function phi now. Those are inequalities of third order. Our main conjecture is if you have 8 parameters, R1, S1, U1, 2, S2, and so on, 8 parameters, we conjecture that this inequality is true. Of course, we cannot prove it. It seems pretty difficult. But we can prove in some particular cases. In 2 particular cases. In fact. The first one is when this is taking place. It's a particular case of this general inequality. And so we proved that this is greater than this, and for 3 parameters. Because of those conditions over there, we have only 3 parameters, and this inequality actually took place. It is proved. Another one is this other case, and we have 4 parameter inequality. So this multiplication is greater than this entity here on square. So that's what we done in this paper. And now the proofs of it, for example, and so on. The method of proof is very interesting. We took this auxiliary function, and for this function, we make all calculation there. The main lemma. Okay, it is not important anymore, but now we are going to application of this. Application in information theory. can go. Yeah. So we can here, this is those probability distributions, as it say, greater than 0, and the sum is equal to 1. This is the set of finite or infinite. And in information theory is very famous, the Caesar's F divergency. CF, this is the note, it means this, is this sum. Q and phi are two probability distributions, and this quantity, the sum, is Caesar's F divergence, where F is some convex function. Convex function. And now we have examples. If we take x on alpha now, not s, alpha is greater than 1, we obtain alpha order divergence is defined like this. And this is the notion of it. Then, this is important because it is there included in this definition of Renyi's order divergence and Charlie's order divergence. Very important. This is also important, is Kullback-Leibler divergence. Kullback-Leibler divergence, if we put that f of x is x logarithm of x, this function is convex, or if x is greater than 0. And we obtain you understand this? How we obtain this? How you say? Caesar's F divergence is defined sum QE F PE over QE. Isn't it? This is the definition. And now, if you take the F is x of x, this is convex function. Why? Because when you calculate second differential, you get this. First is logarithm is plus 1, second is 1 over x. And this is greater than 0 because x is greater than 0, because of this logarithm. So, this is convex function. And if you put it there, you obtain what? You obtain this Kullback-Leibler divergence for this function. It goes like sum QE F is this. Instead of x, we put P over QE. So it's P over QE and a logarithm x is also P over QE. And what is this? This is join, and it's a sum P logarithm P over Q. This is Kullback-Leibler divergence. This one. Another example, if you put that f is this, you obtain this Hellinger distance. Hellinger distance also primary notion in information theory. If you put this is also convex, you obtain chi-square distance. Chi-square distance is very important in economy of services, and so on. Because the time is passing, this quantity is called Bhattacharya coefficient. This quantity is always greater than 0 and less than 1. It's called sometimes Bhattacharya constant. Okay, and because of application of these above moments, we make here yes. We already detailed 9 approximation of this Kullback-Leibler divergence with those functions f1 and f2. They both functions depend only on Bhattacharya constant and chi-square distance. So this is the f1 is this and f2 is this. It was known before that k is greater than this. Pardon. K is, yes, greater than this, -2 logarithm of this. But now, because we know of this above, we put this positive remaining, you see. So this first inequality is now become much stronger. For the second inequality, it is now the k is less than this, but we make it with this minus even lesser. Because of the knowledge we make above. So, I will stop now with this and I go to S divergency, if you agree. How to come?
Yes, you have 15 minutes, you can.
So this is another thing.
This one?
Yes, this is hard. Yes. Okay. I prepare some slides for this workshop, and it is on symmetrized S divergency. It's it now. How you move it now? But it doesn't make the next be obtained divergency. So it could be treated, this divergency, as a more general thing that Kullback-Leibler divergency. And as I said, Tanea showed that this divergency is convex in it. But we know that it is in fact logarithmically convex, which is stronger property. And it included, as we said, Kullback-Leibler divergence, and more than this, it included Hellinger and chi-square distances as particular cases. How we obtain it? Let's see. If you put that S is equal to 1/2 over there, you obtain this, and this is equal to this, and this is a square minus square, and this is exactly 2 Hellinger distances. Also, if you put that S is equal to 2, we obtain this, and this is equal to this, and this is 1/2 of chi-square distance. So all of those measures are included into the notion of S divergency. Tanea says it's continuous and convex. We said it is a log-convex function. We say divergency. And now we came to this notion of symmetrized divergency. Symmetrized divergency, it means what? It means that there is symmetry when you have P and Q and P. There is a symmetry. We said it is symmetrized, but it is rarely happen. Of all of those measures, we have only this one as the symmetry property, this Hellinger distance. Hellinger distance. Where is the definition? Okay. Is that? So h square of PQ is the same as h square of QP. It's just because of this square is the same. So it is symmetry, there is symmetry. For example, there is no symmetry because there is, but it is not the same if you divide by Q or by P. So it is not equal, no symmetry. For example, in chi-square distance. The only one who has symmetry is this Hellinger distance. But we could make symmetry by force. You see, because if we construct this another function us to be the sum of those two. this function US is symmetrized. For this one, this relation is true. US of PQ is the same as US as QP, with the sum of those two. Another way to symmetrize is to make a product. This is the other way. This Y, way, V, is defined as a product of those two. Also, they have a symmetry property. So, idea of this symmetrizing comes originally from Kullback and Leibler, because when they investigate the function, the divergence, here you remember, they in fact they work with this symmetrized divergency, something like this. And now it has a name as a Jeffrey divergence that originally comes from Kullback and Leibler. So this idea of Kullback and Leibler is now we make this also not only as a sum as they did, but also as a product as well. And what are the results? You see, the main theorem of this article is this, that U, as this is the sum, is positively continuous, then it is all convex for each S, then the graph, when you make a graph of S, is symmetric with respect to the line S is equal 1/2, symmetric, and then the lower point is when S is equal 1/2, and this is exactly 4h squared. So it's monotone decreasing in this interval, and monotone increasing in the other interval. This inequality took parts for each S and T. Main properties of the sum. And now you will see that main properties of the product are almost the same. Also log convex, also symmetric graph, but now this constant down there is 4h squared. Also decreasing there, increasing here, also this inequality as well. That's my results for those symmetrized. And finally, if we normalize, it means that we treat this as a mean, not only plus, but divide by 1/2. And this V, not the product, but the square of the product. This is normalizing. And there we have this inequality, nice one, for both of them. Now it is the time.
Okay, try to finish your presentation.
Okay, that is for this. We have some appendix. This is also interesting for convex functions. You remember this is the definition of the convex function, and all these those theorems we make proofs based on this property. This is the theorem C. So we have subcosed interval, and this function f there is the sum minus, it's also the difference. between objects. And what is important, this function, this property. The maximum of this function is exactly f of AB. You have interval AB. Maximum is obtained at points A and B. So this is always less than f of AB. This property of convex functions is proved there, and took my part into proofs of this above theorems. And now I will finish really. So this is references. Caesars, Hardy and Littlewood is classic. Jeffries is the symmetrized Kullback-Leibler divergency. Kullback and Leibler, their mind works. And some of our papers, one is from statistical bits letters, and the other on this, another in the factor mathematics. So that's it. Thank you very much for your attention.
Thank you for a nice presentation. And now it's time for question.
Yeah. The last, you have a maximum.
Excuse me. Bitte?
Last function, you have a maximum.
Maxim?
Yeah, the last one.
Yes, I will make it.
Yeah, last. So this means that the function fst is concave, isn't it?
My ears doesn't work properly.
So this function is concave, isn't it? fst.
F at AB.
fst. You get the maximum at AB, isn't it? You have a maximum of fst.
F is defined of this interval.
Yeah.
So
So
for
if this
each
function
S
is
and T,
concave,
max of this function is exactly this.
yeah. So it is concave at AB.
So what is the question?
Is you have a maximum of that thing.
Yes.
This means that the function, you have a objective function fst is concave or convex.
You
Is it
understand?
convex or concave?
The function.
Your function, fs t, is it convex or
Concave.
This is question.
This is my question.
I don't understand.
If you have a look, if you have a function convex, it always has minimum, isn't it?
Minimum.
Yeah.
But this is maximum.
It's maximum, so it's concave.
What is the question?
Is the function is concave or convex?
Actually,
You write
bitte.
Yeah, I will.
Put it
Write
on the
it
table.
Can I read this one, please? If you have a convex function,
Yes.
then it always has a minimum.
Yes.
Okay? My question is, your function is st,
Yes.
so this is concave or convex? This is my question.
This function there.
Yeah,
This.
two
But
variables.
who knows?
So-
I don't know.
so-
Are they concave? Maybe they are not this.
This
not
is
this.
my question asking it.
Huh?
This
It is only positive. What we know about big F is positive.
Yeah, this I know.
But
that.
is it concave or convex? We don't know.
So it is.
Took some example and see by
You can
yourself.
see. Yeah. Okay, that I will take. This is I asked.
No. They have not this property, not at all. They have not this property,
Yeah.
this function.
Yeah. Always it had a property.
Okay, this
Yeah.
property is okay
So you have a
for a
maximum.
convex function. But this function f is not convex, not concave.
Yeah. This is what my question was.
Yeah, this is good.
The
Another
second question is about your conjecture. Yes, please.
Okay.
About your conjecture in the last lecture, you gave this conjecture that.
No more questions?
The second.
Yeah.
Thank you
second
very much.
question is this one.
Okay, the second question.
Yeah. Second question is this one. You have a for the two variable. I just write down this one. You have an x1, say y
Another question.
over 2 plus you have a u plus v over
Yes.
2, isn't it? So then you went to the three variables. So can we have the same thing, x plus y plus w? You take the mean because these are the mean.
Uh-huh.
So you have a u plus v plus z over 3. If you write down that conjecture in this form, it may be easy to solve it. Your conjecture.
But I don't.
Yeah, this is your mean. For two variables,
Okay.
you have mean.
Okay.
Then you introduce three variables.
Okay, of course.
So,
This.
my question is, if you do the parallel to this one, this is the mean. And if you take this mean, how will your conjecture will go?
Yes, but
Yeah,
does
this is
it
the conjecture.
go to this theory? That's
Yeah.
the problem.
So this is mean, can this things can be incorporated and included in your theory?
Mm-hmm.
This is it.
Okay.
Conjecture.
Okay, thanks.
Okay, thank you. Let us thank Professor.
Yeah.
Again.
Thanks a lot.
And the second speaker. Okay, we have the second.
Come back.
Yeah. Second speaker, Dr. Shah Muhammad from Mathematics Department. Coming.
Screen is here.
Screen go to view. So,
I think it's here. Yeah. Full screen. I think it should be somewhere here. Here, click on it.
yeah, it's okay. Okay. You need to use.
Maybe little bit.
Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning and welcome everyone on my presentation. I have selected a general topic. I didn't have the complete idea of the audience. I thought maybe some students are also coming, but all the faculty members are here. Anyway, this talk is about the importance of mathematical softwares for teaching of mathematics. I am Dr. Shah Muhammad, Assistant Professor at the King Saud University, Riyadh. My talk has the main contents which you can see here. I will introduce medical softwares. Then I will explain why the use of software is important for teaching of mathematics. Then I will show some examples of uses of softwares in calculus, differential equations, linear algebra, and numerical analysis. And finally, I will conclude my presentation. Mathematical software. There are many software which are available in the market, which we for the use in mathematics. First of all, what is a software? A mathematical software is a software which can use to model or analyze, calculate numeric, symbolic, and geometric data. Any software which has any of these abilities, we call it a mathematical software. There are many, as I said, starting from the very simple and graphic calculators. There are computer-aided computer algebra systems like Axiom, Maxima, Gap, Science Lab, and there are many others. There are also some general purpose softwares which can also be used for mathematics, like MATLAB, we have Maple, we have Mathematica. These are the commonly used general purpose softwares for mathematics as well. You can see some the icons of some of these softwares. This is Maxima, we have MATLAB, we have Mathematica, and we have Maple. Some of them are open source, some are commercial. It depends, like Maple and MATLAB, Mathematica are the commercially available softwares. We have to buy them, and the computer algebra system, many of them are open source softwares. We can just freely download them, and we can even change them. I have on my next slides some how to move. Start again?
Yeah, okay. You start.
These are the interfaces of two commonly used general purpose software, the MATLAB and Maple. On the left you can see the interface of Maple. We have a couple of packages on the left hand side. It's not really readable from the here, but many symbols, many commands are built in, and they are available inside these buttons. When we click on this, we see a list, and we can use any of those available under the list of commands. Similarly, there are some buttons available at the top, which are for the for different objectives. For example, we can run, we can save our work, we can run our code by using those buttons. There are very many and they have different features. Similarly, this is the interface for MATLAB, and it has a few windows. This is the editor window, which is the main window where we can write our code. Similarly, there is a command window. We can see over here. This is command window. We can directly run various built-in commands and perform various operations over there. This is a command history. Whatever we do in the command window is stored in the history. We can anytime access it. Also, there is a this is like memory, command memory. Whatever variables we declare in our in the command window, they are available. They are visible over here. Their nature and their sizes. This window has several buttons at the top, and they are also used to run, to save, and to open and new files, etc. They have different functions like that. So the interface is not very complex for students. Also, it's quite easy to use them and to understand them. Then we come to the importance of mathematical softwares. There are many importance which we can talk about. I have just selected few of them. The important and the first one is the creativity, which means the divergent thinking or deviation from the conventional thinking, or kind of out-of-box thinking. Like this is a very important feature of human brain, and I think it's the most important activity or skill of human brain. Also, it is necessary for the development of new things. If we don't have creativity, we will not produce anything new. For students, it's very important if they use the software. This will improve their creativity skills, because they have a software and they have also the knowledge of the theory, and they have to relate it, like in the software, how can they explain their theory, how can they implement their theory. So in a way they will think from a different perspective, and it will help them to use their knowledge in a different way, like not just writing, but it's in the form of presentation, in the form of a visual, visual entity. Similarly, this will help them to comprehend effectively the complex and abstract ideas. Usually, students say mathematics is boring or mathematics is difficult because many things which we explain to them in words or in descriptive form, or we explain to them on blackboard, they are just symbols, numbers, not much visualization. But with the help of software, we can explain that whatever we write, it has a visual effect, and you can see them on computers in visible form. So this will help them to understand the complex and abstract ideas of mathematics in an effective way. Similarly, when they relate different concepts in the form on the software, this will help them to develop new concepts, and also they will learn new things from this. It is time saving because when we do things on the paper, it takes a lot of time. But when we do things on the computer, we just have to change, like do little changes and just press the enter button, and then we see the results very quickly. I think if we need to do something on paper, on board, in half hour, we can do it like in few seconds on the computer. Also, it's lasting for longer time in memory. Whatever we listen or whatever we read, we forget quickly than whatever we see. Whatever we see from eyes, it remains in our mind or in our memory for a longer time. So these are some of the importance of the mathematical software as far as the teaching of mathematics is concerned, and I am mainly talking from the teaching of mathematics at the undergraduate level to the engineering students, the mathematics students at the start of their university time. Now I will show some I'm sorry, still again we have to restart it.
It doesn't need a file. You can,
Yes, I think it should have been in the PDF form. I have just selected some uses of MATLAB for the commonly used courses which majority of the university students take, like calculus, differential equations, numerical analysis, and linear algebra. The core of calculus is the curve sketching, as I guess, because we have functions, we have curves everywhere in the calculus, and it's always important for the students to learn about the curve sketching. Now, curve sketching is quite difficult if we ask them to do on the paper, but if we ask them to do with the help of software, it's way easier, and they will find more motivation because it is faster. For example, in curve sketching, we have main idea which we need. The first one is domain and range. Then we have the idea of the increasing and decreasing function. Then we have the concavity and point of inflections. Those concepts, as I know from my understanding, students have a lot of difficulty with them when we ask them to plot the graph and then find out the points of inflection, the domain and range of the graph. But if we use the software, then we have we can quickly explain from the results, visual results, what is concavity, what is maxima, what is minima, what should be the domain, what should be the range of the functions. And this is I'm talking about the variety of functions, because instantly you can plot any function, you can plot any curve on the graph with the help of the software, and you can instantly show them, even in half of your lecture, you can show them plenty of examples, which is not possible with the help of board or by sketching on the board everything. So, for example, I have here the graphs of tangent x and secant x, and now if I want to explain to them what is concavity, what is the point of inflection, what are the like maxima and minima, domain and range of these functions. So it's very clear. I can very easily show them what is the domain, what is the range, why it is so, which points are not included in the graph in the domain, which points will not be included in the range. Similarly, I can explain to them the asymptotes easily from here. So in a way this makes things easier for the teacher also, and also it helps students to follow it quickly. For the in MATLAB we can use the commands like limit, lim, diff, int, plot, 3D, surf. With a limit we can find the limit of any function. Even the L'Hopital rule is also incorporated, so if we have any function, we just write the syntax of the lim command and then we press enter, we will get the result. Also in the symbolic form. It's not just MATLAB doesn't only give us the numeric data, but it also gives us the symbolic results. Similarly, with diff, we can differentiate any function, any given function, and we get the result and result of the derivative. We can use MATLAB for the evaluation of the indefinite integral as well as the definite integrals with int command. Similarly, we have plot for the function plots, and also we have plot 3D for the and surf for the 3D surfaces and plots. I've also shown example for the about the to explain the point of intersection or the solution of a system of algebraic equations. So we can explain the meaning of the points of intersection or the meaning of the solution of the given algebraic system in a graphical way. Whatever we get the solution of these equations will obviously the point of will be a common point of these lines represented by each of the equation, and it's visible over there. Next we have also we can use MATLAB for the linear algebra, numerical analysis and differential equations. Commonly used commands for linear algebra, which we can use inverse. You can find the inverse of matrix of any order with just enter the matrix first and then use the syntax of inverse command. It will instantly show you the inverse, the result of the end result, because otherwise finding an inverse, it's time consuming. Even for the 3 by 3 matrix it takes few minutes. So with this one instantly you can find the inverse of any function, any matrix. Similarly, determinant can be find for any matrix. We can solve. We can use this solve command for the solution of any algebraic system of equation of any size in a very quick time. We have poly, like it can be used to find the roots of any polynomial, whatever degree of polynomial it is. You can just instantly find the roots of all the roots of the polynomial. Similarly, eigenvalues can be used with this I command. You can find the eigenvalues of any matrix in a short time. Also, we have uses in numerical analysis. These are commonly used commands OD2, 3, OD4, 5, which are based on the Runge-Kutta methods or the Taylor methods for the solution of numerical solution of the ordinary differential equations. Similarly, we can write down the command, we can write down the program for the bisection method, for the secant method, for the fixed point method, and then we can solve any transcendental equation or any equation with the help of we have to just change the input of the function, and then we can find the roots of that equation. And also, as I earlier shown, the plot command, we can explain to the students quickly that what does the root of the equation mean with the help of graph, because it's basically the x-intercept of the graph of the given equation. If we solve it for the independent variable, so the roots can be found by using the program for the bisection method or any other method for finding the roots of an equation. We also have uses in the differential equation. With the help of dsolve, we can solve any differential equation of any order, or also we can solve any system of differential equations, of whatever size, with the help of dsolve. We also can find the Laplace transform of the given functions with the help of Laplace. So all these are few. Of course, there are plenty of built-in commands in MATLAB for the linear algebra problems, numerical analysis problem, differential equation problem. This is just few to give an idea. And for the students, it could be very easy if they do some paperwork and then they want to see the results. They can very easily, in few minutes, they can check all their results with the help of software if they are useful, if they are used to using this. I will conclude my talk with some concluding remarks. As we have seen that there are many softwares which are easily available from the market or from the internet, or many open source softwares can be easily downloaded and used by any user, and also the commercially available softwares are also not very difficult to access, because the institutions usually they have the copies and students can use them. If somebody wants to buy them, they are also not much expensive. The use of we also talked about the use of softwares for making the understanding of complex concepts easier and long-lasting. We have shown some uses of the commonly used general-purpose software MATLAB for the calculus, numerical analysis, and differential equation for the students of undergrad level. This is all about my talk. So, if you have any question, you are welcome. I have a class, consecutive class from 10 to 12. So I have to leave out.
What are the drawbacks of these things?
The drawbacks of these things are because, of course, there should be check and balance. If students are really just using these things, then they will not be paying attention to the theory. So it's up to the supervisor or up to the instructor that there should be a balance with the theory and with the use of the software. So I think the